Hello, calculus students. Welcome to part 3 of 2.1. We are continuing to find limits algebraically, and so far we have only learned about direct substitution, where we literally plug in what x is approaching into the function. If we get a numerical answer, which we have a lot, numerical answers are just any, real number, including 0, then great, we're all done, we found our limit. But if we get the indeterminate form of 0 over 0, the limit could still exist, but we need to get there in a different way. And today is the first of a few ways that we can get there by factoring and canceling. So this is the path that we're mainly focusing on today. And as always, if we get undefined, meaning like 4 over 0 or something, that means that the limit does not exist. This is undefined. If you are not feeling confident with factoring, then I do suggest that you watch the factoring and overview video that I have linked, and that is also in the playlist right before this video, just to get you ready for factoring, since I'm not going to do a review of factoring in this video. All right, our first example, we have actually two different limits that we want to evaluate with the same rational function here. Note that this is a factorable numerator. But before we even get to that, I just want to use direct substitution because that is always what we want to do first. So if we use direct substitution, we are going to plug in -1 here. So if we plug in -1, we'll have this. So I plugged it in, we'll have, when we plug in -1, we'll get 0 over -5. This is a numerical answer. Please do not get this confused with indeterminate form or undefined. It is neither of those. This is 0 out of a number. That means 0. 0 is a viable numerical answer. So this limit here is actually 0. We do not have to employ any other algebraic methods to find this limit. And we can see that really the only issue would be if we plugged in 4, right? Our denominator would have an issue. So let's actually take a look at that issue over here. So we're going to plug in 4. And the first thing, again, that we have to do is direct substitution. And when we do that, we'll have 16 minus 12 minus 4, which is 0, and then 4 minus 4, which is also 0. So this is an issue here, right? This is indeterminate form, which I will abbreviate as IND. I'm not going to circle it because it's not our answer. All that indeterminate form tells us is that there is a possibility that this limit still does exist, and we have to use another method in order to find what that limit is. So let's do that. This video is about the method of factoring and canceling. So let's factor and cancel this, and I will do that in pink. So I'm going to start again. So I'm going to say the limit as x approaches 4 of our original function. And what I'm going to do is factor it. So, I don't like that. I'll just do equals. All right, so when we have our numerator here, this can factor into x minus 4 and x plus 1. And I'm going to still write the limit there because it still technically is a limit. All right, and then our denominator can't factor. There's no GCF there. I noted that there was not a GCF in the numerator. I just went right for the 2 parentheses there. All right, now what we can see is that this x minus 4 cancels because the same factor is in the numerator and denominator. And so if we plugged in 4 here, we still would have 0 times 5, right? So 0 over 0. We'd still have indeterminate form. So factoring itself doesn't get rid of that issue of indeterminate form. It's the canceling that does. So once we have that canceled, this is really the limit as x approaches 4 of just x plus 1. And we can plug in. Now we can go back to using direct substitution here. When we use direct substitution, we're going to plug in 4. And when we plug in 4, we'll get 4 plus 1, which is 5. Now let's explore why this works here. All right, we saw that this function really was broken down like these 3 factors here. It was, I'll do this in orange, it was x minus 4 times x plus 1 all over x minus 4, right? And then we canceled the x minus 4, so we were left with just x plus 1. Well, what is x plus 1? That's just a line. It's y equals x plus 1. It's our function, it's a linear function, and it hits the y-axis at 1 and has a slope of 1. Now, the only issue is, because we canceled out this, our domain had a restriction. Our domain is every single value except 4, because 4 would make this denominator 0. And so when we write the domain, our domain goes from negative infinity to 4, skips over it, and then 4 to infinity. So what we have in our graph is we actually have a hole where x is 4. So if x was 4, right, we would get to 5. That would be the next point here on our line. But we actually have a hole there because we can't equal that. It's not in our domain. It would give us 0 over 0. But we can hit every other number on this line, every other value, every other point. And so that's what this function is here. It is the line x plus 1, but a hole where x was 4, because those canceled out. They're not, x is 4 is not in our domain. And so we can see that the limit when x approaches 4 from both the left and the right is still 5. The limit's the y value we get close to. But if we tried to plug in 4, we had an issue, right, indeterminate form. And so we had to factor and cancel in order to find what that y value would have been. Now, if we take a look at over here, which this went away, but I don't know why that went away. But remember, we did see that this ended up giving us, when we used direct substitution, 0 over negative 5, which was 0. Let's make sure that was right. As we approach negative 1 from the left and the right, our y value is in fact 0. So in this example, I wanted to show where we always have to use direct substitution first. Sometimes it yields a numerical answer, and that's our answer, done. Sometimes it'll yield indeterminate form, and therefore we have to employ another algebraic method in order to find the limit. In this case, that's factoring. So we factored, canceled, and then replugged in our value, no longer an issue of 0 over 0 after canceling, and we found our limit. And here I'm showing you the graphical reason of why it works. All right, our next example will be quick. I'm not going to do the graphing thing for every single one. Let's plug in 3. That's always our first step. We'll use direct substitution. So when we plug in 3, we'll have 3 times 9, right? 27 minus 27, which is 0. And then we'll have 3 squared, which is 9, minus 15, which is negative 6, plus 6, which is 0. So I'm not showing a ton of work here, but that's indeterminate form. All right, indeterminate form has been proven. Now we can go into the algebraic method of factoring. So we're going to have the limit as x goes to 3. And then let's factor our numerator. We can pull out the GCF of 3. That's always the first thing you want to look for. Our denominator is a quadratic trinomial when a is 1. Two numbers that multiply to 6 that add to negative 5 are negative 3 and negative 2. The numerator, what's left here, is a difference of squares. So that can factor into x plus 3 and x minus 3. Note the 3 still stays out front. And then all over x minus 3, x minus 2. All right, if we use direct substitution here, we still would have 0 over 0, because what gets rid of it is not the factoring, it is the canceling. So the x minus 3's can end up canceling. And then we can plug in, we can use direct substitution from here. All right, so that's what we have left. So this equals the limit as x goes to 3 of 3x plus 3 over x minus 2. Now we can use direct substitution. When we use direct substitution, we'll plug in 3 for x. And we will have in the numerator 3 times 6 and in the denominator 3 minus 2, so our final answer is 18. So here was a case where we got indeterminate form, the limit that tells us the limit could possibly still exist, so we used factoring and canceling to find what it was. All right, evaluating the limit here as x approaches 1 of this rational function, we want to first plug in 1 using direct substitution. So we'll have 1 minus 1 over 6 minus 6, which is 0 over 0. It is indeterminate form. Therefore, we're going to use factoring. So we'll have the limit as x goes to 1. We can't factor the numerator at all, but the denominator does have a GCF of 6 that we can take out, and we'll be left with x minus 1 over 6 times x minus 1. We can cancel the x minus 1s, and so we're just left with the limit as x approaches 1, and we have a 6 in the denominator. But we do still have a 1 in the numerator. Recall that anything divided by itself is really 1, and so this fraction here that we canceled is 1 over 1. So technically, we do still have a 1 in the numerator. I'm using this example because I'm showing it specifically because I want to show that when we're left with nothing in the numerator, it's not really nothing. We do still have a 1 there. So a common error students will make is they'll just write 6. But be careful because it's 1 over 6, 1/6. So now we can use direct substitution, but wait, where do we plug in 1? Nowhere. This just means that no matter what we're approaching here, the limit is 1/6. All right, let's try this one here. So we want to first plug in pi. When we plug in pi, we'll have pi times the sine of pi minus pi all over pi. Getting hungry. All right, what is the sine of pi? The sine of pi is 0. So we'll have pi times 0 minus pi all over pi, which is going to equal 0 minus pi, so negative pi over pi, which is negative 1. So in this case, direct substitution yielded our answer. Now let's try this same function, but approaching 0 instead. So let's do the limit as x approaches 0 of x sine x minus x all over x. When we use direct substitution here, we'll have 0 times the sine of 0 minus 0 all over 0. So no matter what the sine of 0 is, it is actually 0, but that doesn't really matter here because it's 0 times it. So we'll end up getting 0 over 0, which, as we've said for the millionth time, is indeterminate form. So the limit could still possibly exist. And what we are going to do here is use factoring, and I'll do that in blue. So we'll have the limit as x goes to 0, and then I want to factor this. So in the numerator, the GCF is x, so I can take the x out front, and I'm left with sine x minus 1. This is really x times sine x. We just don't need to put the times here, but these are two different factors being multiplied. Okay, all over x. All right, the canceling comes here. X over x can cancel. So when we plug in 0, using direct substitution, we'll have the sine of 0 minus 1. We don't have a denominator anymore. The sine of 0 is 0, 0 minus 1, and that is negative 1. Just so happened that these two answers are the same. I didn't necessarily plan for that, but I just wanted to show the difference between plugging in. You always want to do direct substitution first, and it can yield the answer, awesome. And when it yields indeterminate form, you have to factor. But I wanted to show this example mainly because I don't want us to forget about trig. So we can still use factoring even when there's trig functions involved. Okay, this next example is asking us to evaluate the limit as x goes to 0 of this function here. And again, we want to first plug in 0. When we do that, we can clearly see that we'll get 0 minus 0 all over 0. So I'm not going to show all that work, but this is indeterminate form once again. So let's try to factor it. I'll factor in pink. So we'll have the limit as x goes to 0, and then our GCF here. What can we take out of both of these terms? We could take out a 2 and an x to the 4th. So our GCF in our numerator is 2x to the 4th. We're left with an x to the 1st minus 6 all over an x to the 4th. Now what can cancel is this x to the 4th over that x to the 4th. When we use direct substitution here now, we're going to plug in 0. So we'll have a 2 and then 0 minus 6, which is 2 times negative 6, and so our limit is negative 12. All right, this is our very last example. Again, we want to first plug in and use direct substitution. So when we plug in 4, we'll have 4 minus 4 over 4 squared minus 16, and this clearly will yield 0 over 0, indeterminate form. One type of indeterminate form, but it's the one we're working with right now. And then I'm going to factor it. So we'll have the limit as x goes to 4. The numerator can't be factored, but the denominator is a difference of squares. Now this looks like it wants to cancel, but these in fact aren't the same. And so I want to cancel this, and it actually can cancel, but what we have to do is a little bit of fancy math magics here. And I want to make this look like x minus 4. So I'm going to do a little trick here in blue in the numerator. I'm going to take out a negative 1. And let's see what's left here. Well, what do I have to multiply this negative 1 by to get back to a 4? A negative 4. So this is what I'm doing here. And then negative times what will get me back to this minus x? A plus x. Then I can rewrite what's inside here. Instead of negative 4 plus x, I can write it as x minus 4. All right, and I didn't do anything to the denominator, so those are quotes showing that it stayed the same. And then here, it'll stay the same. So I did a little fancy maneuvering in order to flip something around. You're technically taking its opposite, basically. So we pulled out the negative and made it look like x minus 4. This blue numerator here is equivalent to this original pink numerator, just a little fancy maneuvering. The reason we did that fancy maneuvering is so we could get the x minus 4s to cancel. Now let's see what we have left. We do still have that negative 1 in the numerator still left here. That negative didn't cancel. And we're left with x plus 4 in the denominator. Upon using direct substitution now, we'll get a numerical answer when we plug in 4. So our limit evaluates to negative 1/8. And that is the end of this video about factoring and canceling to find limits algebraically.